Hello again. Today we're going to be talking about the Earth's motion and the effect that the Earth's motion has. Throughout this entire semester so far, we've been in Unit 1, but specifically today we're going to be looking at material that's in Unit 1 of your book, specifically Explorations 1 and 2. You may notice that this particular presentation is not color-coded, and that's because the note guide that I gave you is far more specific in what you're supposed to write down. So, the Earth is moving. This should not be news to you. The Earth has two main motions. The first motion is its rotation. The rotation of the Earth is essentially it's spinning on an axis. The revolution of the Earth is its orbit or its trip around the Sun. Today we'll be focusing on the Earth's rotation. One of the first effects of the Earth's rotation that we're going to be talking about is that it makes objects appear to move in our skies. If you're in a car and you look at another passenger as it moves, you and the passenger looking at each other don't seem to be moving. It looks like everything is flying past the car. That's the same phenomenon that causes things to appear to move through the sky. As the Earth rotates, the objects outside of the Earth, in other words, space, appear to be moving across the sky, and that, of course, includes the Sun. So things appear to rise in the east and set in the west. That tells us that the Earth rotates counterclockwise. In other words, if you were hovering in a spaceship above the North Pole, it would appear to move in a counterclockwise fashion. Take a look at these pictures here. As the Earth spins this way, this is a bird's eye view of the North Pole. If the Sun was over here, we would expect the eastern coast of the United States to get the sunlight first because it's rotating towards the Sun. And as we see, that's exactly the case. Their time zones are ahead of us. The most obvious effect of the Earth's rotation is our daily cycles, or in other words, day and night. It's also our basis for measuring time. One full rotation of the Earth takes 24 hours. That is also known to people as the passing of a day because it is the spinning of the Earth that we use to mark a day. If we look at this picture here, given the shading on it, we can assume that the Sun is in this direction. That's because this is lit and this is dark. The boundary between the light and the dark areas is known as the terminator. And so it's this line here. And that also marks where we know on Earth to have sunrise and sunset. So right now, the east coast of the United States in this picture would be experiencing sunrise. The way that I know that is the Earth is spinning towards the right, or in other words, counterclockwise. And as it spins, this portion of the Earth is going to be spinning into the daylight. So it's sunrise. Here we see an actual picture taken from space. That's our terminator. Since the Earth is spinning towards the right because it's going counterclockwise, we know that this is sunset because North America is spinning into the darkness. Since rotation causes day and night, and that is our measurement of a day, we also use it to measure time. As you know, the Earth is spinning counterclockwise, which means that this side of the Earth is nighttime and that side of the Earth is daytime. Well, we know what hours we associate it with daytime and nighttime, but how is that? Why is that? Throughout the course of daylight, we know that sun rises in the east at the horizon, rises to a peak, and then sets in the west at the horizon. That is our view from Earth. If we were to, again, look at a spaceship hovering from the North Pole, we would see that this person standing here at noon would be located at this spot on Earth. In other words, the most direct spot towards the sun. Can't spin into it any closer to it, and it's not going to spin away from it. It's right in the middle, most direct spot. That is what we define as noon. We have to use noon because sunrise and sunset changes with the season. The position of the sun at its peak is referred to as transit, and we can either think of it from the observer's position on Earth as the sun's peak for that day, or once again this location. That generally lines up with how we measure noon on our watch. So that means in order to describe noon as always being that position as the Earth rotates, noon is going to have to change. We adjust for that using time zones. The time zone makes it so that at that location, noon is always close to transit. I say close to transit because if you imagine here we are in the central time zone, this pink shaded zone. We are towards the eastern edge. And so at our noon, I say close to transit because if you imagine here we are in the central time zone, this pink shaded zone. We are towards the eastern edge. And so at our noon, the transit position is going to be right in the middle of that time zone. So for us, noon on the clock is not going to be exactly transit's going to be in the middle of this time zone, but time zones make it so that it's about noon. And you may notice if we count the time zones across that there are 24. A quick guess will tell you that there are also 24 hours in the day, so that the world is dividing up into zones separated by an hour. That's also the rate that the Earth is turning. So in that hour, the Earth turns 15 degrees because 360 divided by 24 is 15 degrees. So what does all this mean for how we measure time? As I've already explained, this position here is noon, or in other words, transit. That means that on the opposite side of the world, in other words, a half of the way around, or 12 hours, if this is noon, then that makes this midnight. So midnight is also defined as a spot opposite of transit. If the Earth is spinning counterclockwise, that means that this section of the world is experiencing two things. The first of which, if this is noon and the Earth is rotating this way, then this portion of the Earth is afternoon, and this would be the terminator, which means that this is sunset. Depending upon the seasons, we're going to estimate 6 o'clock at night. If this is midnight and this is noon, that means that here, this is after midnight and this is before noon, which means that this is the sunrise position at the terminator. Take a moment and label these on your notes. Of course, the Earth's rotation causes not only the sun to appear to rise and set, it also causes anything else in space to appear to rise and set, including other stars and constellations and planets. As I've mentioned, the Earth rotates around an axis. That basically means that there is a fixed plane around which the Earth rotates like this. And because of that, as the Earth rotates, it appears that all of the objects in space, in other words, the celestial spheres, rotate around the poles. So directly above the North and South Pole, 90 degrees declination, are what we call pole stars. A pole star is just the object directly above the poles. In the Northern Hemisphere, we have Polaris. It's also known as the North Star because it's always directly above the North Pole. It points north. The Southern Hemisphere isn't as lucky. They currently don't have a pole star and won't have one for quite some time. As the Earth rotates, all the objects appear to move around the pole stars, and depending upon your latitude, some objects move around the pole stars and they're so close to that pole star that it never seems to set. We call this circumpolar. As I mentioned, your latitude determines how this looks. So some stars in some areas are all circumpolar, and in other areas only the pole star is circumpolar. At the poles, the celestial sphere would have this perspective. A person would be standing up top here, and their perspective of the celestial sphere would be something like this. As the Earth rotates, it would seem like all of the stars are moving around the sky, basically parallel to the horizon. So at the poles, everything is circumpolar. As you looked at the stars, if you could see them in a time lapse, they would make trails horizontally across the sky. If you were looking directly up, everything would be making a circle around Polaris. This is an actual picture taken time lapse very, very near the poles. Of course, the North Pole, there's no land, and so this particular picture was taken very, very high latitude, but not directly at the North Pole. Here in Wisconsin, we're at what's known as the mid-latitudes. In other words, we're between the equator and the poles. Specifically, Wisconsin's about halfway between the equator and the poles. As you hopefully remember, the altitude of Polaris is about equal to a person's latitude. Our latitude here is about 43 degrees, so we can expect Polaris to be about 43 degrees up in the sky. As objects orbit Polaris, because of the apparent rotation of the Earth, we'll see that some objects, depending upon how close they are to Polaris, are never going to set. So in Wisconsin, these are the ones that are circumpolar, and they're going to be the ones that are closer to the pole. So for us, circumpolar constellations include the Little Dipper, in other words Polaris, the Big Dipper and Ursa Major, Draco, Cassiopeia, and Cepheus, those that are closest to the poles. If we could view the sky in time lapse, it would look something like this, with this being Polaris. And all of these stars would be our circumpolar stars, because no matter how the Earth rotates on this night, those stars are never going to rotate out of the darkness, revolve out of the darkness. On this diagram, those stars would be these. Looking east, with Polaris being somewhere up here, we would see the horizon look something like this. The stars would come off the horizon at a diagonal. At the equator, the celestial sphere is quite a bit different than the way we experience it in other parts of the world. At the equator, it feels just the same way as it does anywhere else because of gravity, and you stand straight up as zenith. However, at the equator, what's really happening is you're standing on the side of the Earth. And so your celestial sphere is this portion of the sky. And so in reality, it's looking something like this. What's at your horizon are the north and south poles. And zenith is straight up in line with the celestial equator. What that means is that everything appears to rise directly off of the horizon, go straight up, and then go directly down in the west. So therefore, the only thing that you can see is the pole star, Polaris specifically, and that's usually right at the horizon, so most of the time people at the equator don't have any circumpolar stars. And their sky would look something like this in time lapse. Here's one pole, here's the other pole, and looking directly east or west, everything would come straight off the horizon like this. Take a moment and draw in the horizon line similar to the one that's here so you can see the path of the stars. These would be facing, all of these pictures would be facing directly east or west. I'm hoping I didn't confuse you too much by my explanations. I think that this animation might help. So to start with, you'll notice the latitude is set to 90 degrees, or in other words, the North Pole. As we animate this drawing and we see the stars moving, we see that they're moving completely horizontal to the horizon, this green line. If we show the star trails, you'll see that they're all horizontal to the horizon. And if we look at it, change our perspective, we see that looking at zenith, this would be down from zenith, everything is making a circle around Polaris. However, if we set our latitude to what we are here, we're pretty close to 43 degrees. And if we move our horizon so that we can see it from the side and add a bunch of stars, we see that objects appear to move diagonally from the horizon. Notice the stars in blue are not dipping below the horizon. Instead, they're the circumpolar stars that never set. The same thing would be for the southern hemisphere at negative 43 degrees in pink. If we look at the view from above, we see now that they are diagonal across the sky. Here we see the view from the equator. As I animate the stars, we see that they rise off one horizon, come up to the top, and then set at the other horizon, and that the poles are directly at the equator. If we see the star trails, we see that they're moving up and down directly. From above, we have straight lines. The final thing I want to point out with rotation is that, of course, we're rotating while we revolve. That presents a problem with the way that we measure a day. When we measure a day from space, it seems fairly obvious, a 360-degree turn of the Earth. We call this a sidereal day, and so if you were looking at the Earth from above, again down in a spaceship, you'd see that it just made a complete turn, just like the hand on the clock. It would be very obvious. That actually doesn't take 24 hours. It takes 23 hours, 56 minutes, and about 4 seconds. However, on Earth, when we measure a day, we're not looking at it from above, we're looking at it by where the sun is. And in that one day, the direction of the sun changes because the Earth is revolving around the sun. And so when we measure from the Earth, we have to take the revolution into account, We call this account the synodic day, or in other words, the solar day. And so when we measure from Earth, we measure by the apparent position of the sun. So the transit from noon to noon. That amount of time is 24 hours. That's because it actually goes a little bit more than 360-degree rotation. It goes about 361 degrees because it has to rotate a little bit more to account for where the Earth moved in that day. The Earth rotated about 1 degree. 360-degree revolution, 365 days in the year, it's about 1 day. And so the sun has to appear in the same exact spot. The Earth has to rotate a little bit more to account for that extra degree. This becomes much easier for me to understand if I see a diagram or an animation. So let's start with the diagram. Measuring as from a sidereal day, it would just be the Earth spinning 1 turn. Now this is greatly, greatly exaggerated. This is, of course, a lot more than 1 day, but it makes it easier for us to see. So that next day, the Earth has moved a little bit in its orbit. As it moves in its orbit, if it were to do just a 360-degree turn, the 360 degrees would be measured by where it's facing in this direction. Because the Earth's position has changed, it has to move a little bit more. Let's look at an animation. A sidereal day is easy to see first. If we advance 1 sidereal day, it just means the Earth going around 1 turn. If we were to advance a whole bunch of sidereal days, maybe 20 or 30, there's 10, there's 20, there's 30, we see that each time that little person marking a location on Earth is facing directly to the top of the screen. But notice, they're not facing the sun anymore. In order for that person to experience noon, they'd have to turn quite a bit more. Now that was 30 days. I did that to make it more obvious to see, but in each day, that's what happens. So a solar day, or in other words, sidereal or viewing from Earth, would look something like this. Every day, it turns to the sun. So if we did a bunch of days at a time, it's always going to face the sun. Notice, once again, that that's not the same position as it started from. When it started, it was facing directly to the top of the screen, and now it's facing at a diagonal. That's it for our discussion of rotation. Join us in the next video where we'll talk about the Earth's revolution. As always, make sure you come see me if you have any questions.